So this is a joint work with George Furtunis, who recently defended his PhD in Athens, and this is actually part of his work. So, in case you fall asleep, and of course it happens to all of us, I will just spend a couple of minutes to tell you what you're going to be missing, just so that you can fall asleep without having any remorse. The paper is about a quite low-level optimization technique that takes advantage of unused space in pointers in architectures like AMD64 in the context of a compiler for a subset of Haskell. So neither the problem nor the solution that we have in the paper is very deep, and I felt that it would be not very interesting to replicate what we have in the paper. So I was thinking what would be more interesting to show in this talk, and I had some alternatives in mind, but most of them, I guess, would not be accepted by the session chair. In any case, what I will be talking about really is first an outline of the techniques that we use in this particular compiler for the subset of Haskell that I was telling you. These techniques are the ones that enable the optimizations that we have in the paper. And this is going actually to put all this work into context. The techniques I'm talking about are the intentional transformation, which maybe you haven't heard before. It's natural, it's a quite old thing, and I will explain it from the beginning. And something that is called lazy activation records, which again is going to be something crucial for what we follow. And this is the first part of the talk, probably the longest part of the talk. It's not in the paper, and the rest is whatever from the paper I found interesting enough and worth presenting here. So this is going to be it. So starting from the intentional transformation. The intentional transformation is something that dates from the 1980s and the 90s. Most of the work about it has been done in Canada and mostly by students of Bill Wage. The intentional transformation is considered an alternative technique for implementing functional languages like Haskell, for example. And the way it does it is by transforming functional programs to Dataflow programs. So Dataflow comes into picture, and I will talk a little bit about Dataflow. In Dataflow programming, a program is just a network, a Dataflow network, or a directed graph, if you want. And in this network, the nodes are processing units that do some computation, and there is also a flow of data across the edges of this network. And the way in which this works is in every processing unit, in every processing node, whenever the data that it is waiting for are available, then this node is activated, produces some output, and then this output possibly enables the computations in other nodes, etc. So this was quite popular in the 80s because it gives you a very implicit parallel nature. So it doesn't enforce an order of evaluation, and you can compute this in a parallel way if you have the appropriate hardware. So back then, there were a number of Dataflow programming languages researched, and a number of Dataflow machines, Dataflow architectures researched. But I'm not going to be talking about this very much here. Now, from the 90s, interest in Dataflow programming started to decline. And the main reason was that these Dataflow architectures were not very popular and were not very efficient in comparison with mainstream architectures. For example, we know that Moore's law says that the uniprocessors double their frequency every couple of years, and this used to hold very well at that time. So Dataflow architectures could not compete with that. And this resulted in declining interest, as I was saying. But today, interest is sort of renewed, at least some of us think that way. And there are several reasons for that. First, Moore's law is not, doesn't hold very much anymore for uniprocessors, at least. On the other hand, there is quite cheap commodity parallel hardware in the form of multi-core machines or distributed machines that talk to each other. And on top of that, there are programming languages and programming models that are quite similar to the Dataflow programming model. Even, for example, MapReduce can be perceived as such programming model. So this sort of makes me feel that maybe this idea should be considered again nowadays. So, just a small example to understand how this intentional transformation works. Let's say we have this very, very small functional program. And the idea is the following. In the first step, we identify all the calls in this program. For example, f applied to 3, f applied to 7, and we eliminate the calls. We erase the actual parameters, and we replace them by applications of a particular operator that we call call. So this becomes like that. F of 3 has become call 0. This 0, 1, etc. are just numbers. We number the calls and we tag them by, let's say, integer numbers. Also, we remove the formal parameters from the definitions. And of course, this doesn't work because you have just erased the actual parameters. So we have to put them back somehow. The way in which we put them back is we collect them and we add definitions for the formal parameters, like they were separate definitions in the program, which look more or less like this. So x, which was the formal parameter of f, had two instances, one here and one there, which are collected these actuals there. And of course, now we have a complete program, but we don't know how to run it because it has some operators that we don't know yet. It's calling these actuals, we don't know what they do. So we need a model for executing this, and this is the intentional programming model, which is called deduction usually. And actually what it says is that you cannot just compute the value of an expression independently from anything else. You need a context. You need something that's called a context. And in this very simple setting, the context is just a list of natural numbers. So let's imagine that we have an evaluation function, eval, which takes an expression and it takes a context. And what it does, it evaluates E in W. Let's see what this eval does for the call and actuals, because for everything else, eval is quite simple, just does point-wise evaluation in the context. So for call, what it does is that it takes the tag I and it prepends it to the context. So you get one more element in the list. And in actuals, what it does is it removes the first thing from the context, from the list. And this I, this tag, is what makes it select the expression to evaluate next. So from all the alternatives in the actuals, I is the one that picks the expression to use. And in this way, if you run the result of the transformation I showed you before, this is what you get. I will not go into the whole example because it will be boring again, but let me just point out that this red thing there is evaluated to this, so the call adds 0 to the context. This blue thing here is evaluated to that, so because we have 0 here, we are picking the first thing in actuals, that's why we get 3. Whereas on the other hand here, in the other call, we have 1, and we pick 5. So that's what we get, 5 over there. This is pretty much the idea for the intentional transformation for first order programs. And if you come to think about it, what you're really getting is a data flow program. This is a data flow program because it doesn't have any functions or anything. You just have values to be computed in some context. And if you run it with the contexts, you're getting the result of it. And back in the 90s, researchers have shown that this can be generalized to higher order programs, not just first order programs. But the generalization had some complexities and some problems. So the general idea here was that if you have a program with a function of order n, then you don't just need a simple context like the one I showed you. You need a context with at least n dimensions. And by n dimensions, I mean an n tuple of lists, not just one list, at least n lists. And each dimension has its own colon actuals operators. And these work and give you the result that would be right. So for example, this program, which has a second order function, double takes a first order function as a parameter, can run with this model and results in what you would normally expect. But there are a couple of problems here before you can apply this to, let's say, a Haskell compiler. The first problem is that it's not easy to support user-defined data structures, user-defined types. The intentional transformation knows nothing about user-defined types. It just uses primitive things. So this could not be translated. And the other problem is that you cannot apply the transformation if your higher order program contains partial applications. So this example is very, very similar to the one I showed you before, but instead of inc, increase by 1, it has add 1. This add 1 is a partial application. So whenever your higher order program contains a function closure, a non-trivial function closure, this cannot apply. And of course, these were known problems from the 90s. Many people tried to solve them. It was not easy to solve them. It was not possible to solve them today. But if you come to think about it, the second problem, partial application and closures and everything, can be reduced to the first problem by a very well-known technique, the functionalization. And this was one of the main ideas in George's work. So now this takes us to the complete picture for George's compiler, which we call GIC. And if you want to try it, it's on GitHub, and you can go and take a look at it and see how it works for you. So the compiler works for a large subset of Haskell. In the documentation, you will find what's not there and how the progress of adding these things is. The first key idea is that in order to go from higher order programs to first order programs, we are using the functionalization, as I said. And actually, we are using a variant of the functionalization that supports separate compilation, which is very important. This is a quite recent paper. The second key idea is that for taking first order programs to data flow programs, we use intentional transformation. And again, we use a variant of intentional transformation that can handle user-defined data types. This was from last year's Paddle paper. I'm skipping this. And finally, the third key idea, which is important for the rest of my talk, is that in order to have an efficient implementation of the evaluation module for that, we are using an adaptation of something called lazy activation records, which is an older idea, and this is what I will be explaining next. So, the back end of the compiler translates to low-level C code. We could have made it translate to assembly or machine code or anything else, LLVM, whatever. But C code is good enough because you have many good compilers that can take you then to assembly, etc. And it's quite easier. So a Haskell function becomes a C function in this setting, and the C function does not take any parameters, just takes something called a lazy activation record. And also the constructors, which are used for user-defined types, they also become C functions that also take a lazy activation record and produce a very simple thing as a result. So the model, the execution model that we use is actually a push-enter model. When you think of the original function, the original Haskell function that we were translating, what you actually do in the execution model is you push a lar to the memory, and then you enter the function code. And actually, lars, lazy activation records, are the only things that exist in your memory here. You don't have any other representation for data type values. You just have lazy activation records. So what exactly is a lazy activation record? When we see the whole picture, you will probably realize that it is quite similar to the activation record that you had in mind. But starting from the intentional programming context, it is better if you think of it as an efficient way to implement the intentional context. So you had your list of numbers. Yes. The list of numbers is represented as a lar, but also the values of the actuals are put in the lar. And one other thing is that these values there are lazy. So there are three main things in the lar. This is a pointer to the previous lar that makes you the list. These are the lazy parameters that are represented as thanks. And this is one more link that you need, which it's not easy right now to explain exactly what it does. Anyway, so the idea is more or less this, and this is a picture in the memo. So except for lars, we also have thunks, and we need a representation for thunks. The standard representation for thunk has three fields. The first one is a Boolean flag, whether the thing is computed or not. If it is computed, then we need the code pointer. If it's not computed, sorry, if it is computed, we need the value that was the result. And if it's not, we need the code pointer. So this is standard. And of course, we also need a representation for values. Our values can be primitive, like integers, and they can also be lars, which represent constructors for lazy constructors for data types. So now this brings us to the end of the talk, and the next few slides are going to explain the optimization that we are suggesting. So in architectures like AMD64, there is a lot of unused space in pointers. So if you have a pointer, either to the heap or to the stack that is aligned, then the last 3 bits, the least significant 3 bits, are necessarily 0. And also the most significant 16 bits have a very specific value. They have the same value as the 47th bit. And this is in the specification for AMD64. So we were thinking that we could take advantage of that in order to have a more compact representation for large pointers and for thunk. So this is the thunk representation suggesting. We are using the least significant bit for the flag, and in that case we have plenty of space for the code pointer if it's a 0, if it's a 1, so if it's not evaluated. Whereas on the other hand, if it has been evaluated, we put a 0 there, and we can discriminate the two cases of a lazy constructor or a primitive value. We can discriminate them by putting different values 0 or 1 in the second bit. In Haskell, that would not have been necessary because Haskell is a typed language and we don't need this kind of information. Only the garbage collector that we have will become much simpler if this information is there. So, pretty much that was all the technical information that I was about to talk to you. And we have a number of benchmarks. We are comparing two things. You can find the details in the paper. The first one is we are comparing against our previous implementation that did not use the compact representation. But it's more interesting to compare against GHC, which is the de facto standard of a Haskell compiler. And we do that with all optimizations enabled in GHC. Yes, please.
Point of order, there is no O3.
Sorry?
O3 behaves the same as O2.
O3 is O2, yes.
Yeah.
So, this means that actually the result of the second comparison does not take into account only the benefits of the compact representation, but it also compares the complete compiler. This is a bit unfair because we haven't worked very much on optimizations in this compiler. We only do two basic optimizations, escape analysis and usage analysis, whereas in GHC there has been a lot of work. So this shows us that the compact representation is much better than the previous representation, even in execution time. Of course, we would expect it to be much better in terms of memory usage, but except for a couple of benchmarks, it is much better even for time, for runtime. And this slide shows that the GIC compiler is in a number of magnitude worse than GHC with full optimizations on. So for most of the benchmarks, it's not more than 3 times slower, and in a couple of benchmarks, it performs equally well or even a bit better. So, in case you just woke up, what I presented is an outline of GIC, George's compiler based on intentional transformation and lazy activation records, and how we take advantage of tagged pointers in AMD64 architecture. The concluding remarks are things that you can easily expect, I suppose. A general point is that we are sort of optimistic because we haven't worked very much on optimizations, and when we do, we expect that things will become much better in terms of performance. There is still work in progress. Probably the most important is this one, that George is intending to add GIC as a backend for GHC. Future work, and thank you very much.
Questions? I'm sure there are quite a few.
Yes. So all of these pointers that you work with are pointers that you create yourself and manage yourself at runtime, right? So even on a 32-bit machine, couldn't you just use a 64-bit pointer representation and put the tag in the upper 32 bits?
Yes, I suppose we could. We could, for example, do the same thing that the Linux kernel does for 32-bit.
Yes.
But we haven't measured that, and we don't know how fast it will be. Maybe it's a good idea to test it.
So the meat of this is sort of basically to be viewed as an alternative architecture for the runtime system, right? So to what extent could you take just work from GHC core and then sort of just do the transformations from there? I mean, maybe
the major problem we would have there is the fact that we now use a lambda lifter, and actually the GHC compiler is based on a super combinator transformation, let's say. So, on the other hand, GHC core uses local definitions a lot.
Yeah.
So when we take this out of the picture, it will be much easier to go from GHC core to GIC, and it will be a prerequisite actually for doing that.
So what you kind of want is to take core just after it's been generated by desugaring,
Yeah.
and then take over from there.
Yeah. If we wait a bit longer, then the transformations that GHC does will end up in code that we will have to undo some of the optimizations because of the lambda lifting.
Okay, and on the back-end part, you might not be aware, but there's a very, very nice LLVM binding available on package LLVM general that might make it easier to...
LLVM is a very, very good option, and we would definitely have used it if it had better support for garbage collection. Garbage collection is something essential for us.
Yeah.
So that's
the main...
a main issue with LLVM. Otherwise, we would definitely have gone there.
Any more questions?
Yeah. So you're really inspired by the Lucid and multidimensional Lucid work.
Yeah.
So now you have a very fast induction interpreter. Do you want to use that to actually implement multidimensional Lucid, or do you want to really stick to structures of Pascal? Because there's some really cool stuff you can do with all those multiple dimensions.
Yes. Actually, the paper that I cited here, the one with the original idea of LARS, of lazy activation records. Sorry, find it. This one. This one can handle multiple dimensions. So I guess you could apply that to Lucid or Glue or whatever dialect of an intentional programming language you want. But to be honest, no, we haven't done it. Actually, I'm not sure how many people nowadays play with intentional languages and how much sense it would make to have a student, for example, to play with that.
Any more questions while the next speaker sets up? Oh, I would have one then, because I'm curious what the overall motivation for your project is. Do you have hopes to beat GHC reasonably?
Well, maybe it's a bit, I don't know, it's a bit childish maybe, but the main motivation was that we had hit a wall several times trying to make the original intentional transformation work for the complete class of higher order function programs. And when it became apparent that it's either impossible or at least it surpasses our capabilities, we ended up with this idea. And this led to, I think, a nice result in the functionalization and also this LAR idea, this lazy activation record idea. And I think, yeah, I'm not very sure that in the end you will end up with a compiler that can actually beat GHC. I'm not sure how compatible the optimizations in GHC or the standard optimization from the functional setting, how compatible they are with the intentional transformation. But it remains to be seen.
All right. Okay.
I'm not 100% optimistic. Thank you very much again.
Thank the speaker again.